Hi everyone, I'm Veronica Lucky, and I'm going to present the work Expressive Pooling for Graph Neural Networks. Message passing neural networks are known to be at most as powerful as the 1WL test in distinguishing between graphs. In order to go beyond this limit, several different graph neural networks have been proposed, like higher order GNNs like KGNN, or subgraph-based GNNs like ISAN or GSN. It has been proved that this kind of more powerful graph neural networks are equivalent to standard message passing on a graph transformation, where this kind of graph transformation involves increasing the number of nodes in the graph, and so they lead to high computational cost. So a natural question arises, is this possible to increase the expressive power while decreasing the graph size? Usually in graph neural networks, the graph size is decreased through the use of a pooling operator. A pooling operator is a function that maps a graph into a new graph with a smaller number of nodes. Every existing graph pooling operator can be expressed as a combination of three functions. The select functions that clusters together nodes into supernodes. The reduce function that calculates the new features of the supernodes, and the connect function that create edges between supernodes. We identified sufficient conditions on the pooling operator such that the pooling operator increases the expressive power of graph neural networks. First of all, we proved that using an injective reduce function and a select function that is more powerful or incomparable to the Basfer element test, then the pool increases the expressive power. Consider, for example, the two graphs below. So G1 is an hexagon and G2 is a graph composed by two triangles. These two graphs are by spiral lemma indistinguishable. Then if you consider a pooling operator where the select function clusters together connected vertices, we end up with the pooled graph which are by spiral lemma indistinguishable. So far we have shown that with an injective red and a powerful cell, we are able to enhance the expressiveness without any condition on the connect function. We were also able to prove that leveraging a suitable connect function can further improve the expressiveness of graph neural networks. In particular, if you consider a connect function that connects together supernodes if and only if they contain nodes that were connected in the original graph, and an injecting function, then there exists a select function and two graphs that are not distinguishable by the Basfer element test, such that the select function applied on the two graphs are equal, but the pooled graph are Basfer element distinguishable. Consider, for example, the two graphs in the figure, and consider a select function that clusters together pink node, and the connect function as defined above. Then the two original graphs are Basfer lemma indistinguishable, while the pooled graph are Basfer lemma indistinguishable. We also conduct experiments on the break dataset. First of all, we tried node-based pooling operator. Node-based pooling operator are pooling methods that just use node representation or topological information that do not go beyond Basfer lemma for the self function. We proved that node-based pooling operators are not able to increase the expressiveness. And indeed, also from our experiment, we can see that none of these methods were able to distinguish graph within the break dataset. Then we consider edge-based pooling operator. Edge-based pooling operator are the pooling operator that respects the hypothesis of our theorem 4.4. In particular, we also proposed a new pooling operator which is called XP, and this pooling operator is constructed using the constructive proof of theorem 4.4. In particular, for each edge, we calculate an edge score using an MLP, and then two nodes that are adjacent to the edge with the highest score are combined into a single supernode, while all the other nodes form their own supernode. XPool serves as a sort of proof of concept in a sense that it shows how even simple operation can satisfy the expressivity increasing criteria that we derived from our theory. We can see that edge-based pooling operator are able to distinguish between graphs within the break dataset, and in particular, our XP is able to distinguish a higher number of graphs within a dataset with a smaller runtime. Then we consider pooling operators that respects the hypothesis of theorem 4.2. So pooling operators with an expressive cell like click pool, curve pool, and data pool. Also, these pooling operators are able to correctly distinguish between graphs within the black dataset. Despite the good performances that this graph pooling operator has, we have to highlight that these methods exhibit the longest runtime. Conversely, XP achieves comparable graph differentiation performances while maintaining a low runtime. So in this work, we proposed and we show sufficient conditions on the pooling operator to increase the expressive power. So we show that it is possible to increase the expressive power of a graph neural network while decreasing the number of nodes in the graph. Thank you.